Okay, so now we get to talk about the bomb calorimeter. This particular setup has importance in chemistry because this is one of the ways in which we find out how much energy is associated with a given reaction. And in the picture shown here, what you can see is that there's an inner compartment, a sealed inner compartment that contains two reactants, specifically CH4 and dioxygen. And the two reactants are present in this inner sealed container. Through this container, we'll have a wire that comes through from the very outside of the big container itself, all the way inside. And the sole purpose here is that we're going to generate a spark that will allow the combustion of CH4 with oxygen to take place. Now, the inner compartment where the reactants are present is itself submerged inside a bigger container. And in this bigger container, we have water, a pool of water of known amount, from which we have a steer rod that's basically steering the water constantly to ensure that any amount of heat exchanged from the inner compartment of the calorimeter to the surrounding compartment, aka the water, is thoroughly and efficiently distributed throughout. Now, in addition, we have a thermometer to keep track of the temperature of the water. All right, so what ends up happening is that we turn on the apparatus and we create a spark inside the inner system. The moment the spark appears in the inner system, the combustion process begins. And now CH4 begins to burn with dioxygen to give you carbon dioxide and water. In the process of this combustion reaction, you end up generating heat. So the temperature of the inner compartment initially generates enough heat to raise its temperature considerably higher than the temperature of the surrounding water pool. All right, now the premise of this setup is such that the heat is allowed to exchange from the inner compartment to the outer compartment, but the outer compartment itself is insulated from the room in which it's located. So basically any heat that's going to be exchanging in the apparatus will only happen from the inner and outer compartments only. So once you generate a higher temperature inside the inner compartment, you will have heat flow going to the surrounding water pool. And as this process continues happening, heat is going to get lost from the inner compartment, so the temperature of the inner compartment is going to go down. At the same time, heat is going to be gained by the outer compartment, so heat is going to, the temperature is going to increase for the outer compartment. And this will continue happening until both the inner compartment and the outer compartment reach thermal equilibrium, meaning that the final temperatures of the systems are exactly the same as each other. All right, at this point, you will basically read the final temperature of the water. You will have recorded the initial temperature of the water, and knowing the amount of water here can yield ultimately information about the energy associated with this reaction. All right, so it's simply the same idea as before. Q hot equals negative Q cold. Or if you want to be technical here, we can say Q system equals negative Q surroundings. And the Q system is technically the heat of the reaction itself. The Q surroundings is the heat that was accepted by the water surrounding the inner compartment housing the reaction. All right, so like the zeroth law of thermodynamics, we still have MCAT on one side equals negative MCAT on the other side. And you want to input the value for the hot substance on one side and the hot substance on the other if you have those pieces of information. Now, sometimes that's not exactly what you have. And so the best that you can do is rely on the fact that you have a pool of water for which you know the specific heat capacity. And for the calorimeter, you also know the specific mass of water present in there as long as the container is sealed. So basically what you can get from this is the energy, the heat accepted by the water, which has to equal the negative of the heat given away by the reaction. All right, so this will allow us to, in essence, find out just the heat directly. If we have extra information, we could find out the heat capacity of the, of some of the substances here, but that's not what we're going to be doing. Instead, we're going to be focusing on the heat of the reaction. And I'm going to show you two examples of how we make that happen. I'm going to once again keep the idea centered around CH4 reacting with O2, CH4 meaning methane. All right, so in this example, I'm saying that 2.757 grams of CH4 combust in a calorimeter that contains a kilogram of water. Okay, so this is the surrounding water um, where the heat is going to go towards. Now, the initial temperature of the water is 18 degrees Celsius, and the final temperature ends up being up in the 54 degrees Celsius range. But what I want to find out is how much energy was released by the reaction in the process of this combustion. And we're going to assume for this problem that the calorimeter absorbs a negligible amount of heat, meaning that we don't consider heat going to the calorimeter. That may not be true experimentally, and you may actually have to first determine the heat capacity of the calorimeter itself in order to account for any heat loss to the calorimeter. But here we're literally being told, don't worry about the calorimeter, assuming it doesn't absorb heat. Alright, so we're going to go with the same premise. Q hot equals negative Q cold. And the Q hot in this case will have to be the reaction itself. Q cold will have to be the water that's accepting the heat from the reaction. So since we don't know the specific heat capacity of the reaction and we don't know the initial and final temperatures, well, we know the final temperature, but we do not know necessarily the initial temperature of the reaction, we really can't calculate Q hot. But what we can definitely do is calculate Q cold. So what I'm doing right here is renaming Q hot as the Q for the reaction, because that's really the heat that we're dealing with. The Q of the reaction is the Q of the hot species. So we use now Q cold to find out the overall heat associated with the reaction. So we have negative mass of water times the specific heat of water times the change in temperature for the water, which in this case is 1,000 grams, aka the 1 kilogram, 4.184 joules gram degrees Celsius for the heat capacity, 54.23 degrees Celsius for the final temperature, and 18 degrees Celsius for the initial temperature. If we carry on the subtraction, the change in temperature, we find out that that is 36.23. Multiplying by the heat capacity and negative mass tells us that the overall heat of the reaction ends up being negative 151,586 joules, or if you divide by 1,000, negative 151.6 kilojoules. This is the amount of energy released when all 2.757 grams of methane combust away. Alright, so I'm going to come back to this point a little later. Alright, but I want to emphasize that this is the amount of energy associated with 2.757 grams of CH4, which if you convert to moles, you'll find out that that equates to 0.1719 moles of CH4. Okay, so I'm going to come back to that a little later. Let me change the numbers a little bit. So this is example 2. Instead of the 2.7 grams, we're going to now use only half a gram of methane. We're still doing the same reaction, but I changed the quantity. Alright, so other than that, the setup is the same. The final temperature, however, now is only up to 24 degrees Celsius, roughly speaking. So when we look at Q hot equals negative Q cold, Q hot being Q of the reaction, and Q cold being negative mass of water times the specific heat of water times the change in temperature of the water, we find out that the Q of the reaction is negative 1,000 grams times 4.184 joules grams degrees Celsius times the final temperature 24.57 degrees Celsius minus the initial 18 degrees Celsius. Carrying on the subtraction gives us a change in temperature of 6.57. Multiplying by the heat capacity, multiplying by the negative mass, yields a value for Q of the reaction of negative 27,490 joules, which if you divide by 1,000 tells you that this is negative 27.49 kilojoules. And this is based on half a gram of CH4 or 0.03117 moles of CH4. Now, the beauty of this is that I'm going to do one little derivation that's going to leave us with one additional factoid of heat in association to reactions known as the enthalpy. But I'm going to save that for the next video. I'll also show you how we use the enthalpy of reaction within stoichiometry. Okay, so we'll stop right here.